we're going to continue with our 7.3 worksheet, and with this problem we're going to be looking at the relationship between the arc length of the circle, the radius, as well as the openness or the radians of the circle. Okay, so for the following question, we're just going to imagine that a bug is sitting on the end of a fan blade and it's going to rotate in a counterclockwise direction. So that's very similar to what we've been doing, 3 o'clock position, rotating counterclockwise. All right, we know that our bug is going to be 2.6 feet from the center of the fan, and you can see the visual here. So that means that our radius is going to be 2.6 feet. On part A, if the bug travels 5.2 feet around the circumference of the circle, we want to know what is the angle measure in radians that has been swept out. So we're going to think about the bug traveling a total of 5.2 feet, but we're going to do it in 2.6 feet increments. Okay, so we're going to start at the 3 o'clock position. We're going to go 1 radius, which is 2.6, which then also gives us that 1 radian measure. So remember from problem number 1 that a radian is the equivalent length on the arc of 1 radius. Okay, so there's 2.6 feet, and we're going to keep going until we've reached that 5.2 feet. So we're going another 2.6 feet. We have now gone a total of 5.2 feet, which means we have 2 radians. Okay, let's go ahead and do one more. So for part B, we're now going to do the same idea, but now we're going to travel 11.7 feet around the circumference. Okay, so we've already done a little bit of it. So we've got 1 radian right here of 2.6. If we do our second one, we get to about right there. And so if you're wondering how I knew when to stop at that second radian, so just remember on the previous unit circle, we looked at those key clock positions, and at the 12 o'clock position, that is 1.57 radians. So the fact that I wanted to go 2 radians means I'm going to go just a little bit past that. Okay, we're going to continue on around our arc. So we're going to go to 3 radians. So another 2.6 feet on the arc, which brings us to 3 radians. Draw those in here. Okay, and again, how did I know where to stop? So remember from our unit circle before, that halfway around the circle was 3.14 radians, so we're going to stop just shy of that. Okay, so if we look at our arc length, we have gone a total of, we have 2.6 plus 2.6 plus 2.6, which gives us a total of 7.8 units. And then we're going to keep going. Here's the 4th radian measure, which is another 2.6 for a total of 10.4 units around. If we go 5 units, so that brings us to about right there. So I'm sorry, if we go about 5 radians, that brings us to about right there, for a total of 13 units. And so notice that we overshot our distance, right? So we want to be, so 4 radians around brought us to 10.4, 5 radians around brought us to 13 feet around the arc. And so we want to be somewhere right in between, and conveniently 11.7 is exactly halfway on that last radian. So we're going to go an additional 1.3. So if we take the 10.4, add our 1.3, or half of that distance, that brings us to the 11.7. So that means we've gone a total of 4.5 radians. Okay, so that is the angle measure that the bug has traveled. Okay, in just a second, I want you to go ahead and pause the video. Okay, so I want you to think about how could we quickly figure out our radian measure without having to draw this out each and every time. Okay, so what relationship can we find between the arc length that we're looking for and the radius measure that has been given? Okay, go ahead and pause the video. All right, let's go ahead and talk about that relationship. So for part A, we had a arc length of 5.2 feet, and we wanted to think about how many radius lengths, so 2.6, how many of those fit into 5.2? So when we think about the relationship that way, that leads us to division. So it's 5.2 divided by 2.6, which gives us 2, which matches our answer of 2 radians. Very similar for part B, we have a total of 11.7 feet. We want to know how many 2.6 arc lengths fit into that 11.7. So we take 11.7 divided by 2.6, and that gives us 4.5 radians. Okay, so now we're going to create, on part C, a formula to help show that relationship between the radian, the radius, and the arc length. Okay, so part C says express the angle measure in radians swept out by the fan blade in terms of the arc length traveled by the bug S and a circle's radius R, right? So this is giving us some variables. So we have our theta, which notice is in radians. That's going to be very important. Has to be in radians, not degrees. Okay, so theta gives us our angle measure. We know that the bug is traveling S, so we're going to let S represent the arc length. So arc length is just meaning that it's what portion of the circumference of that circle. And then the last part is the circle's radius. R represents the radius. Okay, so then using that idea from the previous two problems, I'll use part B as the example. So 11.7 was our arc length. So we're going to say that generically it's going to be S divided by the 2.6 was our radius length. So we're going to say R for that value equal to our angle measure. So that gives us the relationship S divided by R equals theta. So I can take this relationship and multiply both sides by R. So we get S equals theta multiplied by R. So if we are looking for just the arc length, we can take theta multiplied by the radius. And then I can take that formula and divide both sides by theta, which gives us S divided by theta equals our R. And so now, if we know any two of the variables, we can always solve for that missing variable. All right, let's go ahead and put this into practice. So on number 8, we're going to switch it up a little bit. Now we want to find the arc length. So now we're going to find our S value when we know that our radius is 5.1 and our theta is equal to 4 radians. Okay, so I am going to draw a visual and then connect it back to the formula. So if we are at 4 radians, remember halfway around is 3.14, so we're going to go just a little bit past that for our 4 radians. So that means that our theta is equal to 4. We know that our radius is 5.1. And so I'm also going to go ahead and break up these little sections here. So those little tick marks represent the radian. So here's 1 radian, which is 5.1 centimeters. The next radian is 5.1 centimeters, 5.1 again. And then this last one from 3 radians to 4 radians is 5.1 again. And so if we add up all of those, we get a total of 20.4 centimeters. So that is the total arc length from the 3 o'clock position to 4 radians around. So that does match our formula previously, that if we know our radius and our theta, or the angle measure, we can use our formula. Arc length equals theta times r, which means we're going to take 4 multiplied by 5.1. And notice that makes sense. We took 5.1 centimeters and we did that 4 times. So it makes sense to do 5.1 multiplied by 4. Okay, problem number 9, we're going to find the radius length if the arc length is 13.2 centimeters and our theta is equal to 3 radians. So again, I'm going to draw the picture first, and I'm going to mark off the radians. So there's radian 1, there's the second radian, and there's the third radian. And we know that we've gone a total of 13.2. So that's going to be our total arc length, which is going to be the S. We know that our theta is 3. So we're just trying to figure out the length of this radian, which then gives us the radius. Okay, so we're trying to figure out that 13.2 is broken up into 3 segments. So since we're breaking it up, we're going to use division. So 13.2 divided by 3 gives us 4.4, which means that the radius is equal to 4.4 centimeters. Okay, and if we connect it back to our formula, if we're looking for our radius length, that is going to be r equals s divided by theta. So therefore, we're going to take the arc length of 13.2 and divide it by our 3, which is exactly what we did when we thought about our visual. All right, number 10, I want you to pause the video and do that first part on your own. I want you to find the number of radians, right? So we're looking for that theta, and then we'll do the second part together. So go ahead and pause the video and find the number of radians. Okay, so you should have found that the S was equal to 16, the R was equal to 3.2, so therefore we can take theta equals S divided by R, so 16 divided by 3.2, which gives us 5. So we know that the radians is 5. But now notice that there's this second part to the question. It says find the coordinate point x, y. Okay, so remember that if we look at our visual here, the 270 degree mark is the same as 4.71 radians. So if we want to draw the visual of where the 5 radians goes, it's just a little bit past that. So that's 5 radians. And we're looking for this XY position. Okay, and from a previous worksheet, remember that XY is a coordinate point on the unit circle. And the relationship is that this is going to be r multiplied by cosine theta, comma, and then the y is r sine of theta. And so the radius in this example is 3.2 cosine, and then we just found that our angle measure is the 5 radians. So in place of theta, we're going to write 5. So that gives us the x value of our coordinate. And then repeating that for the second part here, r is 3.2 multiplied by sine. We're going to be using that same theta of 5. And so then I want you to go ahead and plug each of these parts into your calculator. So 3.2 multiplied by cosine 5. That should give you a value of 0.908. Okay, and then the next part, go ahead and plug in 3.2 sine 5 into your calculator, and you should get negative 3.07. And so this gives us the coordinate point of where this particular point exists on our unit circle. Notice the numbers make sense. So if our radius is 3.2, that means that this x value is 3.2 here. And so 0.908 exists right about here. Okay, so the end of this circle is going to be negative 3.5 for the y value, and we're going to be just shy of that, so that means that the negative 3.07 is just slightly above that 6 o'clock position. If on this problem you are not able to get these values in your calculator, you definitely want to make sure that your calculator is in radians. So remember, go to mode and make sure that your radians is highlighted. Alternatively, one other thing you could have done is taken this value of 5 radians and converted it into degrees. So let's go ahead and actually do that real quick. So 5 radians, we can convert that by multiplying by 180 degrees over pi radians. The radians are going to cancel, which gives us 286.48 degrees. And then we can use this same formula right here. So we have 3.2 cosine 286.48 for the first value, and then 3.2 sine 286.48. And we get the same answer, 0.908 for the first x value, and then negative 3.07 for the y value. So we get the same answer. Just remember to be mindful if you are in radians or degrees, and if your calculator is in radians or degrees. All right, and then one last question. So a fellow student announced that the measure of the given angle is 1.2 inches. Is this an appropriate measure? Why or why not? So I want you to pause the video and think about this question. Okay, so the reason why we use a degree instead of inches is that if you have someone that has these two rays, right, so we've got this ray down here, and we have a second ray right here. If somebody comes and measures this and says, well, this is 1.2 inches, a different person can come along and measure between those two rays here, which would be a different value. Somebody else could come and measure between these two spots. And so the length would differ for each person that went and measured the distance between those two rays. So mathematicians figured out that instead of measuring it by lengths, to actually measure it as a fraction of the circumference. So if we think about drawing a circle, we want a fraction of that circle. And so that way it doesn't matter how big or how small that circle gets, we're still thinking about it as a fraction of that circle's circumference. So we could say that angles must be measured as a fraction of the circle's circumference cut off by the angle rays. All right, let's go ahead and talk about the summary. So some of the big ideas from this section is to make sure you have that unit circle and know the values at each of those clock positions. Again, put it on a note card and study and memorize those so that way you can immediately recognize that pi over 2 is equivalent to 1.57 radians. Another big idea is converting between degrees and radians and vice versa. So the idea is that we start with our given units, and the idea is we cancel those given units by putting it in the denominator. So from degrees to radians, we're going to take the degrees, multiply it by pi radians over 180 degrees. And then if we convert from radians to degrees, we start with some value of radians. I'm going to say r radians, and multiply that by 180 degrees divided by pi radians. Okay, and then the last one is that relationship between arc length, the angle measure, and the radius. And the letters that we use is arc length is S, the angle measure is theta. Remember, the angle measure must always be in radians for this relationship to work. And then R for radius. Okay, and then these right here are the three relationships. All right, that is the end of video 7.3.